Helium could make up almost half the mass of the atmosphere of giant exoplanets that have migrated close to their star, explaining why there is a mysterious size gap in the scale of these worlds. Over 5,200 exoplanets have now been confirmed, and many of these are larger worlds that orbit close to their star, in some cases with orbital periods that last just a few days. However, transit observations first by NASA's Kepler Space Telescope and now by TESS, the Transiting Exoplanet Survey Satellite, have found a puzzling dearth of planets with radii between 1.4 and 2.4 times that of Earth. Astronomers call this the Radius Valley, and although it seems to be telling us something fundamental about the nature, formation, and evolution of planets, scientists have yet to ascertain what that something is. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. Now, a new take on the Radius Valley from a team led by PhD student Isaac Malsky of the University of Michigan and Leslie Rogers of the University of Chicago suggests that it could signal an increasing abundance of helium gas in the atmosphere of worlds 2.4 times larger than Earth. Worlds of this scale are often described as mini Neptunes, and if they have a rocky core, it's deep beneath a thick swathe of atmosphere. Early in their lives, while still forming within the protoplanetary disk of gas and dust, planets that formed farther out from their star can migrate inwards. The closer they move to their star, the more they are impacted by the star's heat and radiation, a mix of stellar winds and flares that can gradually remove an atmosphere from a planet in the firing line. As this happens, a planet can grow a comet-like tail as gas is stripped away to leave a bare, rocky core. The atmosphere of such worlds is made largely from hydrogen and helium. Jupiter, in our solar system, is a good example of this atmospheric makeup, being 90% hydrogen and 10% helium. However, hydrogen is lighter than helium and can escape into space more easily. Malsky and Rogers' team designed a computer model that simulated a whopping 70,000 exoplanets of different sizes, orbiting different stars and at different temperatures, to see what effect the heat from their nearby star would have on their atmosphere. They found that indeed hydrogen was removed quicker than helium, resulting in the abundance of hydrogen decreasing relative to the amount of helium present. In the most extreme circumstances, some of the planets that they simulated had atmospheres that were over 40% helium by mass. These helium worlds would occupy the bottom end of the higher size range, around 2.4x larger than Earth by radius. Whether they have an atmosphere rich in hydrogen or helium, the heat from their nearby star would still cause the atmosphere to become bloated and expand, increasing the radius of the planet. Smaller worlds on the other side of the Radius Valley, with radii of 1.4 times that of Earth or less, would have lost all their hydrogen and helium and would have no significant atmosphere, limiting their radius to just that of their rocky core. It is possible that having lost their primordial atmosphere, these planets could then outgas a new, thinner atmosphere similar to Earth's. But if they are much closer to their stars than Earth is to the Sun, then they would face a battle to hold onto this new atmosphere too. There are so many weird and wonderful kinds of exoplanets out there, and this finding not only adds a new kind, but may have implications for understanding the evolution and formation of planets in general, said Rogers in a statement, opens a new tab. Getting a better understanding of this population could tell us a lot about the origins and evolution of sub-Neptune-sized planets, which are clearly a common outcome of the planet formation process. These new findings support earlier research that posits that not only do planets lose their thick primordial atmosphere as they migrate closer to their star, this inward migration of multiple planets in a system could lock worlds into gravitationally resonant chains, like peas in a pod. Helium, despite being the second most common element in the universe, was only detected on an exoplanet for the first time in 2018. However, with the launch of NASA's James Webb Space Telescope, JWST, astronomers have a new instrument in their toolkit for detecting atmosphere gases on exoplanets. If the radius valley is truly the result of planets wandering too close to their star and having their atmosphere shock heated into space, then JWST could provide observational evidence by conducting spectroscopy of hot planets with radii of about 2.4 times that of Earth to determine the abundance of helium in their atmosphere. Most astronomers suspected that young, small mini-Neptunes must have evaporating atmospheres, says Michael Zhang, lead author of both studies and a graduate student at Caltech. But nobody had ever caught one in the process of doing so until now. The findings are published in two separate papers in the Astronomical Journal. One is based on data from W.M. Keck Observatory on Mauna Kea, Hawaii, and the other paper involves observations from NASA's Hubble Space Telescope. Together, the studies help paint a picture of how exotic worlds like these form and evolve. Mini-Neptunes are a class of exoplanets, which are planets that orbit stars outside our solar system. These worlds, which are smaller, denser versions of the planet Neptune, consist of large rocky cores surrounded by thick blankets of gas. In the new studies, a team of astronomers led by Caltech used Keck Observatory's near-infrared spectrograph, NIRSPEC, to study one of two mini-Neptune planets in the star system called TOI 560, located 103 light-years away, and they used Hubble to look at two mini-Neptunes orbiting HD 63433, located 73 light-years away. Their results show that atmospheric gas is escaping from the innermost mini-Neptune in TOI 560, called TOI 560.01, and from the outermost mini-Neptune in HD 63433, called HD 63433c. Furthermore, Keck Observatory data surprisingly showed the gas around TOI 560.01 was escaping predominantly toward the star. This was unexpected, as most models predict that the gas should flow away from the star, says Professor of Planetary Science Heather Knutson, Zhang's advisor and a co-author of the study. We still have a lot to learn about how these outflows work in practice. Planetary gap explained? Since the first exoplanets orbiting Sun-like stars were discovered in the mid-1990s, thousands of others have been found. Many of these orbit close to their stars, and the smaller, rocky ones generally fall into two groups, mini-Neptunes and super-Earths. The super-Earths are as large as 1.6 times the size of Earth, and occasionally as large as 1.75 times the size of Earth, while the mini-Neptunes are between 2 and 4 times the size of Earth. Few planets with sizes between these two planet types have been detected. One possible explanation for this gap is that mini-Neptunes are transforming into super-Earths. The mini-Neptunes are theorized to be cocooned by primordial atmospheres made of hydrogen and helium. The hydrogen and helium are left over from the formation of the central star, which is born out of clouds of gas. If a mini-Neptune is small enough and close enough to its star, stellar X-rays and ultraviolet radiation can strip away its primordial atmosphere over a period of hundreds of millions of years, scientists theorize. This would then leave behind a rocky super-Earth with a substantially smaller radius, which could, in theory, still retain a relatively thin atmosphere similar to that surrounding our own planet. A planet in the gap would have enough atmosphere to puff up its radius, making it intercept more stellar radiation and thereby enabling fast mass loss, says Zhang. But the atmosphere is thin enough that it gets lost quickly. This is why a planet wouldn't stay in the gap for long. Other scenarios could explain the gap, according to the astronomers. For instance, the smaller rocky planets might have never gathered gas envelopes in the first place, and mini-Neptunes could be water worlds and not enveloped in hydrogen gas. This latest discovery of two mini-Neptunes with escaping atmospheres represents the first direct evidence to support the theory that mini-Neptunes are indeed turning into super-Earths.
Yeah.